So welcome back. I hope everyone has coffee now, and we can start the afternoon session. The first speaker this afternoon will be Alex Kuzmich from Georgia, and he will talk about the optical spectroscopy of triply charged thorium ions.
Thank you, Michael. First of all, let me thank the organizers for inviting me to take part in this exciting workshop. Happy to be here and tell you today about our work with triply charged thorium ions. I'll tell you about how we trap and laser cool these ions, and also how this kind of called ion chains, dual isotope ion chains, might one day be used for tests of temporal variation of fine structure constant. A sensitive way to test for variation of fine structure constant with time would be to compare the rates at which two clocks are ticking. If the fine structure constant were to change, then the ratio of these two rates would also change. And a number of such tests have been done, most sensitive of them in the group of David Vineland. And now they see no variation, now at the level of 1 part in 10 to the minus 17 fine structure constant change per year. But another way to look for the same variation, essentially, would be using astrophysical setting by comparing the frequency, the ratio of two frequencies of atomic transitions emitted in the lab with the same ratio for light that was emitted in an astrophysical setting, that is, at some point in the distant past, sort of would be in a different galaxy. This kind of measurements have been done by John Webb and Victor Flaumbaum over the past decade or so, and they have used extragalactic light sources such as quasars and looked at the absorption of that light in intergalactic medium. And what they have seen is that what looks like a signal, a variation of fine structure constant. It's not a temporal variation, but the data are sort of better described by a spatial variation with a dipolar angular pattern dependence and a linear dependence of variation on distance. And the size of this variation is approximately 1 part in 10 to the 5, and what it means for laboratory setting, even though sort of they interpret their data as a purely spatial variation, there would also be effectively a temporal variation for laboratory observations if one takes into account that the solar system is moving through space relative to the cosmic microwave background. And so if these recalculations are done, then one would have to compare two atomic clocks with an accuracy of better than 10 to the minus 18 over the period of roughly a year in order to confirm or refute these astrophysical measurements. On the other hand, I will tell you that thorium nuclear clock of rather modest accuracy of 10 to the minus 14 may be sufficient to improve on or sort of to look to shed further light on this astrophysical measurements. So why is it thorium specifically? And the reason for that is that thorium is the only element with a nuclear transition between the ground and an excited state in here, where the energy separation is small enough to be accessible by lasers. In this system of thorium-229, specifically this particular isotope, thorium-229 nucleus, there are two rotational bands, energy bands in the nucleus, and the two lowest of them with spins 5½ the ground level, and the isomer with spins 3½ are separated by only about 8 eV. These levels have the same parity, so a transition between these two levels is a magnetic dipole one, so the lifetime that one expects from this isomer with respect to spontaneous emission to the ground level is of several hours. So the existence of this isomer was first predicted by Krog and Rich in 1976, but the first measurement of its energy was not done until 20 years later, and that measurement came at 3.5 electron volt with a sizable uncertainty, and that measurement stimulated a number of attempts to observe direct decay or excitation of this isomer, which were going on over the next 10 years or so, but none of those experiments have succeeded. And in 2007, there was a new measurement of the splitting between the ground and the isomer levels that came at 7.6 eV and later was revised up to 7.8 eV, that somewhat explained the lack of success in this previous attempts to directly observe this isomer level, in the sense that the all previous those experiments were largely looking in this wrong wavelength range, corresponding to 3.5 eV instead of the new measurement of 6.6 eV. So this new measurement stimulated a new round of interest in thorium, and a number of experiments have been going on trying to observe this isomer level and measure its energy. And a lot of interest in thorium was also stimulated by a couple of important papers. The first, one of which is by Pike and Tam in 2003, which proposed to employ this nuclear transition as a clock. In particular, they proposed to use a triply charged thorium ion as a setting for a single ion clock. And in 2006, Victor Flaumbaum argued that this nuclear transition might be 5 to 6 orders of magnitude more sensitive to temporal variation of fine structure constant and of strong interaction constant. That is something that really stimulated a lot of interest here. So the reason for this enhancement in sensitivity is this. So the two levels, the ground here and the isomer, are separated by about 8 eV, but the separate Strong and Coulomb contributions to this separation, to these energies of these two levels, are much larger. Basically, the nuclear model suggests that both Strong and Coulomb contributions to the energy of the isomer are on the order of several hundred keV, but they have opposite sign, so that they add up to only 7.6 or so. And so basically the enhancement factor sort of roughly is the ratio of these two numbers that separate, say, Coulomb contribution or Strong contribution divided by the separation, energy separation of the two levels. So because of this, this nuclear clock may be more sensitive to variation of alpha than the best atomic clocks. So highlighted maybe here because it may not be more sensitive in principle. It's more precisely maybe to better say that it's likely to be sensitive, but the nuclear models are simply not accurate enough to actually quantitatively give the value for these numbers, and hence we just don't know at this point what this enhancement factor actually is. But fortunately, though we don't know what the value of this number, there is a way to determine this number experimentally, as proposed by Victor Flaumbaum and his colleagues. And the idea there is that, as they've shown, that this expression holds true for a range of nuclear models, sort of with insignificant variation in these two numbers. Basically, the difference of Coulomb energies of the ground and isomer levels are proportional to the difference of mean square radii of the nucleus for the ground and isomer levels, and to the difference of the electroquadrupole moments of the nucleus for the two levels. And and this is something, these numbers can be determined in the laboratory. And so if that happens, then we would simply know from experimental measurements what the enhancement factor in terms of sensitivity to fine structure constant would be. And there are, of course, different ways to measure mean square radius and electroquadrupole moment. One of them is to use atomic spectra, where the mean square radius translates into isomer shift of optical lines, and the electroquadrupole moment translates into a hyperfine B coefficient in optical spectra. So in principle, any charge state of thorium atom would be suitable for studies of this nuclear isomer level, but for precision measurement, triply charged state would be the best. And the reason for that is that thorium is an atom with 4 electrons in its valence shell. So when you remove 3 electrons, 1 is left, and so we have a single electron atom, and we have a relatively simple structure of lowest electronic levels that is amenable to high efficiency detection and laser cooling. As you can see here, we have a 2-level system and a 3-level system that are all sort of suitable for laser cooling and for efficient detection, fluorescent detection of electronic states. And it's also very helpful, as you might see, that all these wavelengths here, 1087 nanometers, all nanometers 690, 984, and this transition here to metastable 7S state at 718 nanometers, all are in the visible or near infrared. And so we can work with laser diodes. And the reason for this sort of circumstance, which is a little bit surprising given that it's a C9 of relatively high charge state, and so one might expect transitions from the ground state in the UV, but there is this phenomenon called Coulomb crossing that is responsible for this. That is, we know that in neutral atoms, electronic states of large angular momentum can be higher than the states of lower angular momentum, but of lower principal quantum number because of electron shielding effect. On the other hand, in hydrogen-like ions, we know that the states with the same principal quantum number will be nearly degenerate, and thorium 3+ happens to be in sort of intermediate crossover regime where this all levels 5F, 6D, and 7S levels are all close enough to provide this experimental convenience.
How strong are these lines?
Pardon me?
How strong are these lines?
Right, that's what. Thank you. So what I was about to say is that sort of the drawback of this scheme is that we have states of large angular momentum. These are f orbitals and d orbitals, and because of this, the overlap of these orbitals is considerably smaller than in sort of typical ions with a line width on the order of 100 kilohertz. So that's a complication, but it's not insurmountable. So this is a sort of electron level diagram for sort of regular isotope of thorium, which is thorium-232, which is sort of most widespread and the only sort of almost stable isotope of thorium. And it doesn't have an isomer level, but thorium-229 does have, and this isomer level shows up as every sort of electronic level of ground nucleus has a copy of itself shifted by the isomer splitting up, and this shaded region represents the current level of uncertainty for the energy of this isomer. And so each of one of these electronic levels sort of can decay down with emission of a photon of about 160 nanometer wavelengths, with a lifetime expected to be a few hours. And conversely, if an atom is in any of these electronic states, for example in 7S state, it can absorb a UV photon if it's resonant to this transition and make a transition to this isomer manifold. And at that point, it would live there for a long time unless you do something else, or it will drop eventually down via spontaneous emission. So, a nuclear transition from 7S ground nuclear to 7S excited nuclear state can be used for a clock that was proposed by Pike and Tam in the same manner as an atomic transition, long-lived transition can be used for an optical clock. And as they have shown in this paper, a number of common clock systematics are cancelled in this, or strongly suppressed rather, in this system compared to optical atomic clocks. Though there are two remaining issues with this level. First of all, the lifetime of each of these levels is about 0.5 seconds with respect to spontaneous emission, electronic emission on this transition with 718 nanometers, and that limits the quality factor of the transition. And also, there is a sensitivity of this transition to the magnetic field due to the differential second-order Zeeman effect. That is, we have a hyperfine structure here that leads to the different hyperfine structure in these two states. So, Vladimir Duba, Viktor Flaumbaum, and Andrei Derivanko, and my group in this paper have proposed instead to use the ground electronic level 5F 5½ of thorium for a clock which does not have either one of these two limitations, since it's a ground stable level, so there is no spontaneous emission issue, and one can use stretched magnetic sublevels, Zeeman sublevels, as the NIST group has demonstrated, in order to get rid of this issue of sensitivity to second order Zeeman shift. So the clock would consist of one ion of thorium-232 and one ion of thorium-229 trapped together, and 232 ion would be used for cooling, sympathetically cooling 229, while clock sort of protocol is run on thorium-229. And because of the isotope shifts, relative isotope shifts of the optical lines in these two ions, one can indeed run continuously cooling on this 232 ion, while the 229 would be serving as a clock. Well, we would use the stretched Zeeman states in order to get rid of sensitivity or suppress sensitivity to magnetic fields. And also, because the lifetime of this isomer level is so long, one would want also to run the protocol both from the beginning of the protocol from both the ground and the isomer level, in order to cut down on initialization time for the clock. And one can see that here's a table of uncertainties, and basically sort of common systematics of atomic optical clocks are suppressed. For example, like body radiation shift is suppressed down to the 10 to the minus 22 level, basically because we have the same electronic wave function for both levels, different only to the due to the isotope shifts, isomer shifts rather, and the different hyperfine structure in the two levels. Also, the sensitivity to magnetic fields is suppressed roughly by the ratio of the nuclear magnetic moment to the electronic magnetic moment relative to optical atomic clocks. And also, the sign is quite heavy, so the sensitivity to second order Doppler shift is also quite low, especially given the narrow electric dipole transitions here. It should be rather straightforward to cool it into the motional ground state. So overall, if the current NIST state of the art in optical atomic clocks is applied, one might expect an accuracy of 1⁻⁻19 or better for this type of clock. So together, combined with the expected sensitivity enhancement for temporal variation of fine structure constant, that kind of system might provide a really promising candidate for these types of studies. So this thorium 3+ ion is also interesting for atomic structure theory, because as you can see here, thorium is isoelectronic to francium, and here is a calculation of the energies of the low line levels in ions as electronic to francium as a function of the nuclear charge. And you can see that thorium is here at the intersection where the ground state goes from 7s as in francium, goes to 5F as in thorium and higher charged ions. And thorium is right at its intersection, so the influence of many body effects is significant. So it's a good test laboratory for seeing that the atomic structure calculations take the many body effects into account correctly. So because of this, a few years ago, we set up to build a system in which we can potentially excite the isomer level in a single thorium ion. This is a sort of a picture of a fourth or fifth iteration by now. Corey Campbell built the first cooling and trapping apparatus for thorium, and together with Alex Radnaev, they have done much of the work that I'll be talking about today. The trap is located in here. Here's a closer look at this. We have typical 4 linear electrodes to which we apply RF voltages for radial confinement, and we provide DC voltages to cylindrical end caps for axial confinement. And we have 4 thorium targets in this column. One of them is thorium metal, thorium-232 metal. One of them is a nitrate film of thorium-232 deposited on an aluminum substrate. And 2 of these targets, these are the 4 targets, and 2 of the targets are thorium-229, these 2 deposit on aluminum substrate. So another important part of our apparatus is a set of 6 diode lasers that do everything here. The three of these lasers, 984, 690, and 1088 nanometers, are used for cooling, for laser cooling on these electric dipole transitions. The fourth 717 laser is used to excite the electric quadrupole transitions that promote the ion into the metastable 7s level, and the 795 and 780 nanometer lasers are used for frequency reference together with a reference cavity. So a few years back, we trapped and cooled thorium-232 isotope, and these are some of the first pictures of our ion crystals that we've got at that point. And the transition to thorium-229 presented a number of challenges. First of all, for thorium-232, we could have grams of this metal. So whereas for thorium-229, we could only have micrograms of this 229 material, simply because, well, there are two issues. The cost was quite significant, but also it presents some issues from the radiological safety point of view. So you might not want too much of this stuff in your lab anyway. And because of this, we had to work hard on improving the efficiency, the loading efficiency. For loading, we use laser ablation. So we use set harmonic of YAG, and we ablate, in this case, it was a solid metal target here with a set harmonic of YAG. It's a nanosecond long pulses, so sort of about a millijoule in energy that hit this target, and all kinds of ions are produced, singly charged, doubly charged ions, and so on. And what we need is to separate and keep only the triply charged ions in order to have them in the trap. And because of the small amounts of thorium here, thorium-229, we had to improve the loading efficiency for the trap. So we went from rather short trap, or sort of typical trap, to a trap of long trap, 20 centimeters long trap, and that's with the goal of capturing more of this thorium-3+ ion. But this trap does have, due to the arrangement of this cylindrical end caps, has a dimple potential in the middle, which allows us to tightly confine the ions while we are cooling them. And so for cooling, we use this 1088 nanometers and 690 nanometers and 984 nanometer light. Typically, we first cool the ions from tens of thousands of Kelvin produced by laser ablation pulse with a rather relatively intensive 1088 nanometer light. We have typically on the order of milliwatts of this light, detuned by 100 megahertz or so in order to do that. And then once the ions are cooled to tens of kelvins, this lambda system, in particular essentially 984 nanometer light of much lower intensity, takes over and crystallizes these ions. So in the first iterations of our experiment with previous traps, we've had to always begin the process with buffer gas. That is, we always loaded the ions from ablation into the trap in an ultra-pure atmosphere of helium. And then now, after switching to a longer trap, we didn't have to do so, and we were able to capture the ions and cool them in vacuum, which provided a number of advantages. First of all, everything is faster because we don't have to put the gas in and then pump it out. And then also it avoids impurities in this vacuum chamber as it's sort of associated with the helium buffer gas. So the process became much faster, and so here's the time-stamped images beginning with laser ablation process of this cooling process, and we see that in about 20 seconds we go from ablation to a large crystallized cloud. And in fact, when we have smaller clouds, few ions, this is even faster. So this works well. But this is all sort of the test of this new trap, all done with thorium-232, as you can see. And in fact, this particular measurement was done with loading from metal. With loading from nitrate thorium-232, it would work nearly the same, but the clouds would be much smaller. We wouldn't be able to get this kind of massive clouds from nitrate. But then, big change was when we changed from 232 sample to 229, because in 232 sample there was no nuclear spin, and so there was no hyperfine structure, so everything was relatively straightforward. Whereas in 229 the nuclear spin is 5½ and combined with large electron spin values here for f orbitals and d orbitals, we have rich hyperfine structure here. And so once we loaded the ions into the trap in buffer gas atmosphere, and so the buffer gas does cool them down from thousands of kelvins down to room temperature, but all we see then in our fluorescence measurements are broadband features of the spectroscopic lines. And so here's a sort of like the hyperfine structures that we now know, and but we didn't know that at the time, and so all of this hyperfine structure was completely covered, sort of hidden in this broad Doppler background. And so without knowing this hyperfine structures, there was no way for us to laser cool the ions, because they would simply accumulate in one of the dark states, so we would just be heating them. And without knowing the hyperfine structure, we cannot cool. So it was sort of a circular problem, which we broke through by using sympathetic cooling. That is, we used the fact that our thorium target contained 1/4 of thorium-232, and so we employed our normal thorium-232 cooling protocol, but at a much slower rate, because now this 1/4 of thorium-232, while we cooled it over the course of a few minutes, had to sort of drag down with itself in phase space, 229 isotope, and but it did work, and we got better at it, and it became faster at some point, and faster, although never, of course, as fast as you would do for a pure sample, and so what we see after a successful attempt, we see a bright crystalline shell of thorium-232 on the outside, and a dark core of thorium-229 inside. And at that point, the ions are at a sort of few Kelvin. There are 229 ions, and or less, and so the Doppler width is on the order of less than a few megahertz. So at that point, we could employ broadband repumpers to cover most of the hyperfine sublevels and scan just a single narrow laser field across resonance and observe individual lines. We observed a number of these lines for the three transitions, 984, 680, and 1088. So these are all of those lines that we observed. But in principle, there was about 1 trillion way to assign these hyperfine numbers to each of these lines. And so we went through all of these possible combinations and found the one with the restriction that these patterns, this energy separation, should satisfy this normal magnetic dipole electric quadrupole pattern for hyperfine structure. We found the combination that had the lowest RMS deviation, most likely combination. And also we used the information we were getting from this optical pumping kind of observations together with angular momentum selection rules to confirm that the found combination was indeed the correct one in that sense. And so once we had the hyperfine numbers assigned to all of these lines, we were able to extract the hyperfine constants A and B for all of the four of the electronic levels that we were addressing, as well as the isotope shifts that we measured, extracted for these three transitions. So in order to determine the magnetic dipole moment and electric quadrupole moment of the nucleus, something we wanted to do from this data, we would have to calculate the proportionality factors between A and B and mu and q respectively. And those are not easy in this to calculate in this kind of heavy atoms, many electron atoms. And usually the accuracy is not nearly as high as you could get in lighter atoms. But fortunately for us, Mariana Safronova has recently developed a method that allows to accurately determine properties of these many electron atoms. Essentially, the method consists of looking at the properties of similar electronic levels in more than one atom, and by analyzing systematics of disagreements between the theory and experimental measurements to be able to predict the properties, atomic properties, much better. For example, the hyperfine constants A and B can be determined with accuracy better than 2%, perhaps even as high as 1% by doing this. And so by using Mariana's calculations of these ratios of A to mu, we were able to extract the magnetic dipole moment of the nucleus that had this value. So it's quite a bit lower than the previous value and more precise as well. So similarly, we used Mariana's calculations in here to extract as an electric quadrupole moment of the thorium nucleus. We also, in the past, we've also used the prior calculations of Julian Berengut and colleagues that had about 5% accuracy, but the extracted value was the same. But now we have 2.5 times smaller uncertainty with this more accurate calculations of Mariana. So our value of electric quadrupole moment that we found is quite a bit lower than the previous atomic value, but it agrees with the nuclear measurements using Coulomb excitation of the thorium nucleus. So once we knew the hyperfine structure of thorium, direct laser cooling of the isotope became relatively straightforward. And in this case, it's also helped by a closed lambda system here that between the f equals 1 a level, hyperfine level here, to ground levels here and here, f equals 1 levels, and f equals 0 level, excited one. So the ions mostly cycle in there, and so the cooling proceeds pretty quickly. And we have this dual isotope crystals here. Here only 229 is illuminated, and here the bright shell of 232. And for smaller clouds, we also see this two isotope crystals down to chains of a few ions. Here's a pure chain of 4 thorium-229 ions. So one aspect of the experiment that we had to take care of, in addition to taking care of dark states, hyperfine dark states, we had to take care of the dark states associated with Zeeman levels. That is, whenever we have angular momentum in the ground level that is greater or equal to the angular momentum in the excited level, there are dark states. And the dark states we can see here by scanning magnetic field. Some parts of the cloud with nearly zero local magnetic field essentially become dark. They do not emit photons with atoms captured in those states. And one way to manage these dark states or get rid of them is to employ magnetic field that is perpendicular to the polarization of the laser field. But in practice, the magnetic fields required were too large, so for this to work well. And so what we did instead, we employed retroreflection of all these laser fields together with micromotion of our ions. This was destroying these dark states pretty quickly, and so as shown here. So we can use this called ions in principle to excite the isomer level. So one might think of exciting this isomer level directly by shining UV radiation. So any of these electronic levels would then make transition to the isomer version of this level. But the combination of large uncertainty of the energy level and together with really narrow transition of this nuclear transition and low intensity of UV radiation in this range of 130 to 200 nanometer range that we would have to search, make it prohibitively long, this approach. So instead, one might employ these electron bridges that between the ground and isomer manifolds that are generated by essentially hyperfine type coupling between the electron spin and the nuclear spin, which provides mixing of levels, of isomer levels and ground levels. And the strongest of this mixing is between the 7s isomer level and 8s ground level, which opens a bridge, essentially an electric dipole amplitude, transition amplitude between the 7p level, ground level, and the 7s excited level. So when we do the sort of estimate the numbers, well, actually the main amplitude was calculated for us by Sergei Forsov and Mikhail Flaumbaum. Then because this transition is much wider than the direct nuclear excitation, and more importantly, because the search range now is shifted from the deep UV into essentially from regular UV into the near infrared, then that makes the search time much shorter potentially, even although still sort of quite challenging undertaking that would be. So as a first sort of step in this direction, we've excited the 7s level with 717 nanometer light. That was done in thorium-232. And so here's the time-stamped images of a linear chain illuminated by resonant 717 nanometer light. As you can see, the ions go dark when they go into 7s level, and then they spontaneously drop down into this fluorescent manifold, and they become bright again. And so when we plot the histogram of the number of transitions that ions that made as a function of transition frequency, we can determine from this resonant behavior the frequency of the 717 transition. And by plotting the number of atoms remaining in the 7s level as a function of the time elapsed after the elimination period, we determined the lifetime of this level, which was in agreement with theoretical prediction. So after exciting to the 7s level, then the next step would be to excite into the 7p, which is the beginning point of the electron bridge. And we've done that as well, again, for thorium-232 isotope. Here the population of the 7s level as a function of frequency of the 269 nanometer light, so nanosecond long pulses that we've used for this. And we see a resonant depopulation of the 7s level. So the next step for us would be to repeat this population steps into the 7p for 229 isotope, and then apply this essentially rainbow from 800 nanometers to 250 nanometers of light in order to excite the isomer transition. And hopefully that will eventually work. So to summarize, we've trapped and laser-cooled thorium-229 in our trap. We've measured the hyperfine structure and extracted magnetic dipole and electric quadrupole moments from these measurements. And we've excited the atom into the 7p 1/2 level, which is the starting point of the electron bridge. We've done it in 232 isotope. So now we need to repeat this in 229 isotope, and hopefully we will be able to excite the nuclear transition. And if that happens, then we could measure the isomer hyperfine structure, which gives you right away essentially the enhancement factor. And this enhancement factor, in terms of sensitivity to variation of fine structure constant, turns out to be large, then it will really open exciting opportunities for this ion. Thank you for attention.
Thank you very much. Other questions?
You may have said this, but the lifetime of your triply ionized thorium, just due to background gas collisions?
Well, it got longest, sort of. I would say now for single ions, it would be sort of, and of course it would be sort of best sort of conditions after best vacuum. It would be on the order of, I would say, 20 minutes. Yeah, but it's certainly not limit. We don't have anything cryogenic and so on. It's just normal good vacuum as of 10 to minus 11.
So is it just charge capture that gets?
Yeah, it's just charge exchange with impurities, and of course that's much more sort of important than for single ion.
You were giving some number for the micromotion effect on your accuracy of the measurement.
Yes.
And is this assuming a huge ion crystal and then somehow the basic micromotion that you
get?
No.
Because of that was a proposal for a single ion, and that essentially just taken the NIST number. It's just a proposal. It's sort of, yeah.
But then this assumes a certain spray field, right? So this.
Right. So for the clock, for that proposal in that context, we were having in mind one 232 ion and one 229. Mm-hmm. And even then, you don't really have to have 232. You can do 229, but it would be really convenient in terms of laser cooling, in terms of increasing the rate of accessing the clock.
So you had that the electron bridge was they calculated about 100 times the normal lifetime?
That was in terms of width. In fact, in terms of the oscillator strength, it's even stronger than 100 times because the wavelength is much shorter. Yeah, so it's a lot stronger, yeah.
Okay, so I guess, first of all, that doesn't depend on whatever the nuclear transition is. It's just a scale factor. Is that right? It's just 100 times of whatever that is.
Well, so you're asking, so clearly we do not know the properties of the isomer level.
Yeah, exactly.
So I think it's fair to say sort of that calculation, there is some uncertainty there on the nuclear properties. So I don't think it's the order of magnitude. It's better than the order of magnitude. So yeah, maybe that's a caveat I should have mentioned. Yes.
Well, no, I was just curious. But then for your clock, that's included in this 10 to the minus 19 estimate.
Right, that's included because it's sort of it's a significant effect. Sort of you can assume any sort of magnetic dipole moment with isomer level. It will be on the order of nuclear Bohr magneton. So that's what this assumption. That's all.
No, I just meant the broadening due to the electron bridge mechanism. Like
or
that's-
broadened into electron bridge
Yeah.
mechanism. Yes, but well, in our clock proposal we don't have this 7s level. It's 1, it's not important anyway. So even let's say it's 100 times roughly, but the lifetime is a few hours. So even if it's 100 times, it's not significant compared to the half a second electronic lifetime.
Could you explain to me how the micromotion destabilized the dark state?
Well, I mean, so in principle, if you have a perfectly iron at rest, then even if you have counterpropagating fields at arbitrary polarization, but still you would have the same two dark states if your orbital angular momentum, the ground level is higher, by 1 and or just 1. So it would be just a different state, but it still would be there. So, but you have a motion there,
So the motion modulates the polarization effect.
Effectively, that's right. The motion effectively modulates polarization, so the ion becomes
you have
bright.
micromotion along the laser beam direction.
Oh, I'm sure we have micromotion. We'll have micromotion everywhere.
Yeah.
All right, any further questions?
Alex, so there was this original prediction of the energy to be at 3.5 volts or something like that, I forget, and now it's 7 or so.
Yeah.
And they disagreed by quite a lot. So,
Yeah.
so is it well understood why they disagreed? I mean, are you a little nervous that maybe these guys missed too? Or?
I mean, I think in a sense, I would. It's just my approach there that there's a huge risk factor in here. That I mean, it's always you have always to assume that it could be completely different. I mean, this energy. So yeah. So it doesn't worry me that much in a sense. I just take it as overall risk of this project that. Yeah, it could be anything, this number, in principle. So.
All right, let's thank Alex again.